Gord. Warning, this lecture is being recorded. You may want to turn off your webcam if you do not wish to appear in the recording. Recursion. Has anyone heard of this before? Who's used it? I suppose some of you have already done like all the MyPy tutors, but recursion is very, very cool. I teach a whole class on recursion called Comp 3400 where we're limited to programming using only recursive functions. So recursion's a really beautiful, elegant way of solving complicated problems. You can get exceedingly tiny pieces of code that do incredibly powerful things. It just takes a little bit of like time to wrap your head around the strategy because it's a little bit of a mind bend. Okay, so what is recursion? Recursion is when a function calls itself. So any function that calls itself is classified as a recursive function. So this may seem strange because we're using the function itself to define the function. Right, so that's really the hump that we're going to have to get over. So in order to explain a recursion, let's go through memes. Right, there's a few memes that maybe will help us understand recursion. So recursion, it recurs. And recursion, it recurs, and so on and so forth. So like this is sort of like standing in between two sets of mirrors in the toilets, right, when it goes back infinitely. So recursion is a type of like self-reference. Right, so this, yes, this is one way of understanding recursion. Is this a recursion? Is this a recursion? Yes, this is a recursion, right? Because it's self-referential. We're going to learn, so these recursions, the two I just gave you, infinitely recurred. There sort of was no stopping condition, right? So our recursions are going to have to be self-referential, but also eventually terminate somewhere. So we're going to want to have some type of base case. And if you don't have a base case, things will just infinitely recur. So I'm going to write a recursive function with a base case, right? And so on and so forth. And one more for good measure. To understand recursion, one must understand recursion. And this holds more truth than you may think, right? The advice that I give my Comp 3400 class is to trust the recursion works. Like there's always this sort of desire to try to understand the recursion all the way down. And that's somewhat unnecessary, right? You only really need to understand the recursion that you're doing at the time you're doing it, and you just presume that it works. So you sort of have to understand recursion. Notice, okay, so I'm going to tell you about the principle of mathematical induction. Some of you should be taking math right now. So some of you know what the principle of mathematical induction is? Okay, so I'm going to tell the rest of you what it is, but it's sort of a scary looking slide, so I'm just going to like premise it with the fact that like you don't need to know it, you don't need to understand it, we're not going to test you on it. Mathematical induction is basically like, it's exactly the same as recursion, right? It's the same principle is at play. An inductive principle is one that sort of is self-referential. So recursion is essentially an implementation or realization of induction, or the principle of mathematical induction. And this is the principle of mathematical induction expressed with like predicate logic, right? So it means you have some predicate, which we've dealt with them. A predicate is anything that like takes input and returns true or false. In this case, it's a very specific predicate that takes a natural number and returns a Boolean. And the principle of mathematical induction states, if the predicate is true at 0, and if the predicate is true at n, if it follows that the predicate is true at the number that comes after n, the successor of n plus 1, then it is true that for any m, Pm is true. Right? So this is a strategy. So if I give you a proposition over the natural numbers, mathematical induction is a strategy for showing, for proving that that predicate holds for like every arbitrary natural number. So in prose, in English, this means if the proposition is true for 0, and if the proposition is true for n, then it is also true for this successor. And people always get held up on, so when you write a mathematical proof using induction, you write something very strange where you write somehow, assume the truth of Pn, which seems weird, right? Because that seems like the thing that you're trying to assert the proof of to begin with. but you're only asserting the truth of Pn as the antecedent of this logical expression, right? So you have something like if this, then that, right? In order to prove if this, then that, you assume this to deduce that. So you're not actually assuming the thing you're trying to prove, you're assuming it as the antecedent in this expression. So that's all I wanted to say about induction. There's a very classical example to show how to use induction, and it's that of tiling a standard chessboard with these sort of L-shaped dominoes. So if you give me a chessboard, I think a chessboard is, what, 8 by 8? And I give you this L-shaped domino and we remove one of the squares. It is possible then to tile the remaining part of the board with these L-shaped dominoes. A tile means that no tiles can overlap and no square is uncovered, right? So here is like one such configuration. Can we prove that if I give you any 2n by 2n board and I remove a square, that the remaining board is tileable? Right, so this, without the principle of mathematical induction, I don't even know how one would begin to try to solve this problem, but it ends up being a perfect exemplar of how to use the principle of mathematical induction. So I'm going to show you how we can use PMI to prove that any 2n by 2n board can be tiled so that only one square is left uncovered. Okay, so what did I have to do? What did the principle of mathematical induction state? That I have to show that the proposition is true for its base case, for n equals 0. So can we cover a 2 to the 0 by 2 to the 0 board with, that shouldn't be 1, this should be 0. It takes 0 tiles to cover a board with one square, with that square removed. Right, so the base cases always get kind of weird, because it's like, how is an empty tiling a tiling? And I have a slide on that and a story about how I had a big fight with my wife over this type of topic. Okay, so in any case, here's P naught, right? So I have proven that the 1 by 1 board with one tile, if the tile is removed, it takes 0 tiles to cover it. So what's the next thing that we have to do in the principle of mathematical induction? What is the next step here? Yes? Well, we don't have to do n equals 1 because we already have a base case, right? We now need to show if it's true for P of n, then it follows for P of n plus 1. Or is that what you said? I may have not heard.
Yeah, n equals 0, so for n plus 1, so
Yeah, it's more or less correct, right? So I thought you said we have to prove it for 1, and that wouldn't be the case. We need a generic rule that says if it's true for n, then it's true for n plus 1. And that generic rule, given that it's true at P of 0, would imply it's true at P of 1, and P of 2, and P of 3, and P of 4, and as far as you'd like to go. That's sort of the point. It's the typical way of expressing this is like knocking dominoes over. So what I'm going to do is just assume that we can fill a 2n by 2n board. Right? This is sort of the magical thing. It's like, how do we do it? Well, just assume that we can do it on a smaller example, and I'll show how we'll use that to build here. So now, what do I have to do? Well, I have to show that given that it's true for Pn, that I can deduce that it's true for like the board above it. So what's the board above it? That's the 2n plus 1 by 2n plus 1 board. So how can I use our assumption to fill this board? Does anyone have any ideas? Pardon me? Exactly, right? So this is actually 4 of the previous boards, right? 2n plus 1 by 2n plus 1 is actually 2 times 2n, right? So the 2n plus 1 by 2n plus 1 board can be broken up into 4 pieces. What are true about the dimensions of these subboards? What are the dimensions of the subboards here? They're 2n by 2n, right? So what do we know about boards that are dimension 2n by 2n that have one tile removed? What have we assumed? that we can fill them, right? So automatically, we know that this quadrant can be tiled, because that's what we assumed. Okay, but what about the other 3 boards? Well, what happens if I put a tile here? What has happened to those 3 boards? It's as if I removed a square from them, yeah? So by the assumption, all of these boards can be filled. And indeed, you could write a program that just follows exactly this strategy that will actually produce this tiling, right? This is a problem that I give my Comp 3400 students. It would work exactly like this. You would say the 1x1 board, was 1 squared removed, no work is necessary, it's already tiled. I'm going to assume that I can tile 2 n by 2 n boards, and then when you ask me to do like tile the 16 by 16 board, I'm just going to say, put a tile in the middle, and then inductively fill the boards, right? Which we just assume works. So this is sort of strange, but indeed it does work. So what I'm going to do, we're going to program up like a ton of recursive examples today just to show you how it works. But for recursion, you really have to do a lot of thinking before programming, right? Because the inductive step is the magic here, right? Once you get the inductive step working, there shouldn't be much programming left to do. That's one of the advantages of using recursion, is that you have a very compact listing. Okay, so as homework, right, write a function that tiles, right, with distinct tile numbers, a 2n by 2n board so that only 1 square is left uncovered. And if you want to make it easier, you can assume that it's the very first square is always the one that's removed. So here is a 4 by 4 board, and here is its tiling. And I'm going to leave that for you guys to try as some homework. Or maybe I'll even do it next class, depending how much time we have. Okay, so let's take that theory now and try to like sort of pull it into practice, right? So, but it's the same sort of idea is at play, right? We're going to try to write a function by assuming that that function already works for smaller examples. So every recursion, right? So here's sort of the ingredients for a recursion when you're writing a recursive function. Has to have a base case and a recursive step, which is analogous to induction having a base case and an inductive step. So a base case is something in your function which is like defined outright. So like there should be some line in your function which is like, if the base case holds, if we're in the base case, then return this number or this constant, like return this, right? Something that's really defined. And then you should have a line. So if you have a function foo, there should be some line in your function where it invokes itself, where it invokes foo on smaller input. Okay, so the typical example for writing a recursive function in programming is that of the factorial function. Do we know what the factorial function is? So what does the factorial function represent combinatorically? Why do we need it? So the factorial tells you how many ways you can organize n unique objects. So how many ways can you permute 1, 2, and 3? There's 6 ways of doing that. So that's what n factorial is. And I'm saying that because if I'm telling you that n factorial is the number of ways you can permute n objects, how many ways can you permute 0 objects? How many ways are there to order 0 objects? One way. There's one way of organizing 0 things, right? It's the empty ordering. Right, so that's why n factorial is 1 when n is 0, because that's sort of what it's supposed to be calculating. If it wasn't 1, if we made it 0, then everything would be 0. So the definition of that factorial is n times n minus 1 factorial, and if n is 0, it's 1. And this is a great candidate for using recursion, because you see it's sort of already defined recursively. The n factorial is just invoking factorial on a smaller input, right? So it's invoking itself on a smaller input. It has a base case, and those are all the ingredients necessary for doing a recursion. So side note, I already said that. A set of n distinct elements can be arranged in n factorial different ways. Okay, so here's how we can define factorial in Python, right? So def fact It takes n, an integer, it returns an integer. So today, we really need to be aware of this. This isn't my favorite way of checking for 0, but it is the Pythonic way, right? So when I say if not n, what I'm actually asking is if n is equal to 0. We're not supposed to write that. We're supposed to write if not n, right? Because of the truthiness of Python variables. So if you see if not n, you think if n is equal to 0, right? So this says if n is equal to 0, return 1. You can put this thing in an else, but I prefer not to, right? Because when you're programming, you generally want less indents. So recall, if this returns, we're out. It's never going to hit this anyways. So I usually put my base case in an if, and then everything else, I don't put in an else statement. I just find that it simplifies things. But if you're more comfortable putting it in an else statement, then you do you. I'm not here to tell you how to program. Well, I guess I am, a little bit. But stylistically, you get to make your own decisions. Okay, so what happens when I call fact of 0 here? Well, this one's easy. It's going to step into this function with n equals 0. This if statement is going to trigger true, and it's going to return 1. Okay, so that's not really magical yet, because it just called one if statement. If I call fact of 3, what's going to happen? It's going to go into here. This won't trigger, and it's going to return 3 times fact of 2. And then fact of 2 will be invoked, and it's going to call 2 times fact of 1. And then fact of 1 is going to be invoked, and it's going to call 1 times fact of 0, which is 1, so we get back 6. What happens if we call factorial of negative 1? Yes, sir. Infinite loop or infinite recursion. Or in this case, you're going to get something called a recursion error, a maximum stack level. This is also an expression called bottoming out, right? Because like you've missed your base case, and you're like trying to hit the bottom, and you're never going to hit the bottom, right? Because you didn't define a bottom there. So this is relevant. Python has defined like a limited number of recursive calls that you can make. It's set to like 1,000 or something. If you want to go more than that, you have to tell Python to allocate you more stacks, which I'll tell you about at the end. But this is one of the deficiencies of using recursion. The fact that, do I have the slide on this? Yeah, okay, so recursion ends up using a lot of space if you're not careful. Right, because a lot of things get calculated later, right? And I'll show you how that works in this example. So let's walk through how calculating factorial of 4 would sort of work. So factorial of 4 would eventually be made equal to 4 times factorial of 3, which would be 3 times factorial of 2, which would be 2 times factorial of 1, which would be 1 times factorial of 0, okay? So this is, like, you sort of have to imagine this upside down maybe. Because what's happening is we're creating a stack of things that have to be calculated. And once we get to the top, then it starts resolving and like popping from that stack, right? But the fact that we have to like utilize a bunch of memory that then sort of goes away, that can be a problem sometimes. So what this is called winding your recursion. And then what happens after winding is unwinding. So here's the winding phase. And then this is what unwinding would look like. So suppose we wind and we get this. Then Python is going to start resolving sort of the things inside of it. So factorial of 0 becomes 1. And then that becomes 2 times 1, and then 3 times 2, and then 6, and then 4 times 6, and then 24. But the fact that we have to sort of grow and then sort of wind and then unwind is a problem because of the data being consumed from that winding step. But there's ways of like mitigating this. There's a strategy called dynamic programming where you cache intermediate results, and I'll show you at the end of class how to do that. Dynamic programming is like an extremely powerful way of problem solving. It's one of the most used solutions in like sort of programming interviews and stuff like that. Stack overflow. So Python will only allow a finite many recursive calls to be made, right? It was good that it sort of said, you've reached. Okay. So why was, when I called fact of -1, why is this sort of worse than doing an infinite loop? Right? Python doesn't put a hard limit on how many times you can repeat something. Why was it sensible to like have a stack limit here? Yes.
Because every recursion has stuff to memory.
Exactly. Okay. So if I had like an infinite loop that was just printing something, no memory is being consumed to do that. Just processing power. Now, with this factorial of -1, not only were we repeating something, but every repetition required the creation of some stack, some memory. So if we didn't put a hard limit on that recursion, not only would your computer run forever, you would eventually allocate all the available memory on your computer, which is bad. So that's why it's like quite sensible to have this depth limit on the recursion. So in order to increase that stack limit, and I was right, it was 1000, you do have to import this library called system, and then you just say system.setRecursionLimit, and then you can set it to whatever you want, but the system does insist that this stack limit is finite. What is this? Oh, so let's just investigate, right, this stack limit change. So fact of 998, it's this really huge number that doesn't actually show. Fact of 999, stack limit, right? Because don't forget we have that 0. So if I like import sys and I like push it one more, then we can get fact of 9,999. But we can't get fact of -1 is still bottoming out. Okay? Okay, so now I'm going to tell you about the spousal argument that I had, right? That I'm not allowed to mention it anymore. When you're doing recursion, it's somehow really strange what base cases end up being, right? And what the base case is you just define it so that like your recursion works. It's sort of like kind of circular reasoning, but that's sort of the name of the game in recursion. So for example, what is like 2 to the power of 0? 1. But why is something to the power of 0 1? Right? Well, it's because that's what it needs to be in order to satisfy like its recursive rules. And there's like a bunch of examples of this. Like, what is the sum? If I want, like, suppose you have add and you're adding the elements of a list. What should the sum of an empty list be? Well, think of this recursively, right? If we were to write, so like, I'll just do that really quickly. So like I want to write something like summit, which is, oh geez, I'm in the wrong language. Summit, suppose x is a list of int, and I want to return an integer for this. Okay, so we're going to need some base case. So the base case is if the list is empty. We don't know what that's going to do, but otherwise, like this should have a fairly straightforward induction. So I want to sort of take maybe its first element and then sum the rest. So does everyone understand how this works? Right, I'm saying the sum of a list is its first element plus the sum of the rest of the list. Okay, so we could do something like this, and this is what novice sort of programmers would sometimes do, and even in my Comp 3400 class does this sometimes. So somehow say if the length of x is equals 1, then return x's at 0. And this would work. Sandbox. So I can say summit of 1, 2, 3. Oops. Whoop, that's not right. Oh. Equal to 1. Yeah, there we go. Okay, so there's 6. So like, this would be wrong though. Like if you were to write something like this on an exam, this would be wrong. And why would it be wrong? Well, because you've missed one thing, right? Empty list is of type list int. So there's like one thing in here which you should be giving an answer to that you're not. Okay, so that means that this base case is wrong. Okay, so if not x's, which means if x's is 0, or if x's is empty, what should I be returning here? 0, right? Because if you just think what has to happen, if I give Summit a list of like one element, it's like, suppose I have the singleton list 1. This function saying the sum of the singleton list 1 is 1 plus the sum of the empty list. So therefore, what does the sum of the empty list have to be? 0. Okay, so it takes a little bit of practice understanding these sort of weird base cases, but that's how you work them out. So for example, like here's the exponentiation. So we know that 2 to the power of k is 2 times 2 to the k minus 1, or it's like the 2 product multiplied against itself k many times. What does 0 many times means? Well, we know that 2 to the power of 1 is 2, and 2 to the power of 1 is defined to be 2 to the power of 1 is defined to be 2 times 2 to the power of 0, and we can deduce from that that 2 to the power of 0 is 1. So like other questions, what's the product of an empty list? If I wanted to multiply all the numbers in a list rather than add them. 1, because, right? If I'm saying I have the singleton list 7, I'm saying the product of the numbers in that list is 7 times the product of the empty list. So that has to be 1. Right? So they seem strange, some of these cases, like why 2 to the power of 0 should be 1. But they're like that because we've defined them to be like that because they fit into the recursion. Right? We don't want something strange to happen at a base case, right? This sort of falls into the pattern that we want it to be. Okay, so this is the argument I had with my wife. I came home frustrated one day after being incapable of explaining this to the class. And we had this conversation, and like, what would you answer to is an empty basket a basket of fruit? You say no. I say, does it fail to be a basket of fruit? So I say yes, right? Because it doesn't fail to be a basket of fruit. And here's my argument. Like, here's a basket. It has a banana and an apple in it. Is that a basket of fruit? If I remove the banana, is it a basket of fruit? If I remove the apple, is it a basket of fruit? It was just a basket of fruit before I took out the apple, though. Right? So what I'm trying to explain is that an empty basket is a collection of anything. Right? It could be it's a basket of cars, it's a basket of laptops, it's a basket of chairs, right? Because how would you validate that a basket? Okay, here's my pitch. If I gave you a basket of fruit, right? How do you determine that it's a basket of fruit? You have to keep removing elements until you find something that's not fruit, right? So how do you, like, then what is it? You don't have a rule that's saying I need to pull out fruit. You're just looking for not fruit. So is there any not fruit in an empty basket? No. Right? So, yes?
But doesn't basket of fruit imply there is fruit? Basket is
It implies that there's nothing else besides fruit in the basket.
It implies there's fruit in the basket.
is at least one.
False implies true is true, always. Right? That's essentially where this comes. Like, I don't want to argue this semantically, right? Because like the English language is ambiguous like this, but it would be an expression like, if X is in the collection, then PX, right? But nothing is in the empty set, so that would validate as false. False implies anything is true. Yeah.
I kind of see your point here, but I think to be an empty basket, which is a basket of fruit, it has to be a basket that is made for, like, it intends to carry fruit. So, for example, if you have a basket and it's an empty basket, but you intend to put vegetables in it, then it's not a basket of fruit.
No, but I'm just trying to like put English over something that would be like a statement of set theory. Like, if I wanted to validate that, like, the set X, all the elements in X satisfy PX, you would have a statement like, for every X, PX, right? Or X in, suppose I have a set A. Okay, I don't want to get too hung up on this, right? Because, so you want to validate, like, suppose you have a set A, and you want, and you want to validate that every member of A, all right, every member A in A satisfies PA, right? Then you would have some type of statement like this, right? For all A in A, for every A in A implies PA, right? And if this is true, then we can say that the predicate P is satisfied. But when A is empty, right? A in A is false, and false implies PA is true. Right? And that's why I would say it does. But anyways, we one more, then we'll move on, right?
So all you're arguing is the empty set is a subset of any set.
Yes, that's true. Yeah. Oh, yeah. The empty set is a subset of any set. That's another way. But it's like it's that reason for that expression. Anyway, so you can all argue about this on the EdStem if you want. But like if we're like there's some functional stuff in the system that we're going to be talking about next week. There's one of them called all, which checks if every member of a set is true, and all over empty will return true for this reason. So I'll tell my wife that all of you are on her side. That will make her quite happy. Okay, so forget about that. So recursive functions are defined over lists and strings, and we have to worry about sort of like these weird empty cases, right? So the base case over list is typically going to be the empty list. The base case over strings is typically going to be the empty string. And generally speaking, if you're doing induction over some type, you want to find like the smallest thing in that type. Okay, so now let's spend like the rest of class just solving problems recursively. So here's some advice. Ask yourself how you would solve the problem, and like I'm genuine about this being a piece of advice, right? This is how you have to think. I'm going to give you a problem, and you're going to say, how can I solve this problem if I was already able to solve the exact same problem on smaller input? Like, so for factorial was like, how can I get the factorial of 7 if I can get the factorial of 6? Something like that, right? And that's the philosophy we have to have when trying to solve these type of recursive problems. So when in doubt, set the base case to what you need it to be in order for the next small, like if 0 is the smallest thing, 1 is the next smallest thing. So that's the singleton case. So think about what the base case has to be in order for the case above it to work. So here's the first one. Determine if a string is a palindrome. That is, if a word is equal to its reverse. Okay? This is an easy one. So things like race car, dad, mom, these are all palindromes. Like all of these words are the same word written forward as they are backwards. So we'll do it in a few ways. What's like the obvious way of doing this? If I were to ask you how to do this. Any ideas? Yes, sir. Yeah, return x's is equal to the reverse of itself. Okay, so this should already be working. Race car. Perfect. Okay, but suppose I didn't want to reverse a list. How could we do this sort of recursively? Just so we could do it in terms of the strategy that we're trying to work out. What are the two things that we need? Yes, sir.
Look at the first character and last character are the same. Then go one step in further recursion, look at the middle.
Okay, so you're saying I should look if the first character and the last character are the same. And what else?
You should also check that it's not in the string. Check if it's empty string in the return.
Okay. So, okay, you define the correct base case. If it's not the case that x is, that is, if x is empty, then what is it? Is an empty string a palindrome?
Yes.
Oh, okay. But what if I don't intend it to be a palindrome, right? But this is sort of my point, right? This is why I had that conversation. Okay, but so this is mostly correct, sir. What are you missing? So what are we missing in order for this to be recursion, period? We have to call the function from within the function. So what extra piece do we need? What are we missing here? So I've checked, I'm checking if the whole string is a palindrome. I've confirmed that its first element and last element are the same. What else remains to be checked?
That the second element, the second last element.
That the second, like the word, if I remove the first letter and last letter, that what remains is a palindrome. Correct? So I'm just going to say, well, that this is a palindrome. And I think it's something like X is, and is a palindrome. X is 1, 2, minus 1. That, I always forget. That this is right exclusive. So let me just check. Race car from 1 to minus 1. Okay, perfect. So this should work already. Okay, so is palindrome race car? Is palindrome mom? Is palindrome this? False. Okay, good job. So here's another simple recursive routine. Okay, let's do it. Let's just keep moving, keep doing more. So here's the obvious answer, which I went through. Here's the answer using indexing, if you wanted to use indexing instead, and then here's the answer using recursion. Determine if a sentence is a palindrome, ignoring spaces and punctuation. So Al lets Della call Ed Stella is indeed a palindrome if you ignore spacing, casing, and punctuation. Okay, so let's do this one. So this one's going to be a little bit harder. So sentence palindrome. Sentence palindrome. So what's the base case here? So we have to be more careful, right? Because like if I give you question mark, that's a palindrome because we're ignoring spaces. We still have to keep this as a base case, right? We still possibly may get empty, but the base case is more generally, is the string can't have any characters in it, essentially. Like, if you give me something comprised of only spaces or punctuation, then we should say, yes, this is a palindrome. Okay, so you have to remind me what all the string methods are now. Is there a string method for checking if something's a number or a character? What is it? Does anyone remember? So yeah, let's just try to find it. Because I want to know if it's alpha. Return true if the string is alpha. Okay. Geez, I'm gonna do some cheating here. So we have this is alpha. So ABC, that should be true. Great. But something like that will be false. And if I put something like this in here, that should be A. That should be false as well. So really this is if not is alpha, then return true. Right? If you give me a string and there are no characters in it, then that's a palindrome because I'm ignoring all like digits, punctuation, and spacing. Agree? Or disagree, or no? Okay, so what then do we need for our base case? This is a little bit more complicated, right? Because we need to strip the first character. We need to find the first character or last character. It probably would have been easier to use is palindrome. Okay, let's do this easier. There's an easier way of doing this. Let's just use is palindrome like this. Oops. But what I want to do is just return true. X is 1, 2, minus 1. What I want to do is I just want to like strip all the punctuation. Let's take the input and let's clean it first. And then let's give what remains to is palindrome. That seems a little bit better. So what do we have to do here? How can I clean it? So I'm going to just put an H here. This means that it's a helper function. So definition of is palindrome. I wonder how I solved this in the slides. I'm going to go look at it and see, oh, I did something very clever. But in any case, so I want to do something like return, sort of like this cleaned, the helper is palindrome of like the clean version of x. So how do I get the clean version of x? Okay, so what do I want to do here? Have we done list comprehensions yet? Oh no. Okay, so I'll just do it with a loop. Okay, so we have clean x's. That's going to start at empty, so I can say for x in x's, if x is alpha, then I want to, how do I get a lower version of something? Is it lower? Okay, so then I want to say clean x's plus equal x lower. And then otherwise I just skip. So this should, let's see if this is working. Whoops, wrong and. It's tough switching programming languages. Okay, so let's try this.
You need to rename the very last line.
Which one?
H is palindrome.
Oh, thank you. Okay, so let's try his palindrome of, I don't know, some dad with some spaces and some stuff like this. Aha! So let's try this one. Al lets Della call L Stella. True. Great. So that works. I don't think, did I give an answer for this one? Oh, that was supposed to be a homework exercise. Oh, we did it together. Okay, so far all the stuff that we've been doing has been quite obvious, yeah? Like this factorial has been obvious, the sort of palindromes have been obvious, like some of the basic arithmetic is sort of obvious. This maybe is a little bit less obvious. If I give you a list that either contains scalars, numbers, or other lists, there's a procedure called flattening, where basically you remove all interior brackets. So how can we use recursion or any strategy really to solve this one? Any ideas? Okay, so we're just going to go through like exactly the pieces for recursion. So we're going to take in a list, and it could be a list of lists, so I'm just going to say list, and what I want to return back is a list. Okay, so we need a base case and a recursive step. So let's start at the easy place. What should the base case be? What is the smallest object among lists? Empty list. So what should we return in the case of an empty list? How do I flatten a list with like nothing in it? Wouldn't be a string. I don't want to go from lists to strings, right? Sure, return x says or return empty. Right? So here's the empty list. Remove all interior braces. Okay? Here's your empty list back. Now what should we do? Well, it's sort of when we're cursing through lists, the pattern's usually very similar. Right? The base case is empty. And then you want to like take the head of the list out. So I'm going to say this so that we can have the head of the list and the tail of the list. The head of the list is 0. The tails is 1 to the rest. All right, so we usually then want to like recurse on the tail. So it's going to be something like flatten the tail. But what do I have to do in the intermediate? So you're saying like this? Well, I'm not sure, because what if head is a number, like 1? Then I can't concatenate it to it. Take 5 minutes to think about this. Work it out. I'm going to have some coffee. I'm going to stop the recording. You have 5 minutes. I want you to think about this, right? Okay, does anyone have it? Did anyone do it? What did you get, sir? What's your inductive step? What's the magic ingredient here? Nope, no for loops. The recursion is the loop. Not to say what you did is wrong, but let's put it this way. I didn't use a for loop. Did anyone else manage to do this without a loop? Okay, what's your inductive step, sir? What if the head is an integer? Okay, that's better. Okay. So the one key thing here is when we take the head of the list out, what is the head of the list? It's one of two things. It's either like a number or it's a list. Okay, so if the type of a head is a list, I think that's how we say this. Yes. If the type of the head is a list, what do I return? Well, if I pull out the head of the list and it's a list, it needs to be flattened before I can do anything with it. So how do I flatten the head of the list? By calling flatten, right? So this is sort of what I'm trying to force you guys to do. Assume the function is working already when you're programming it. I know this seems very bizarre, but this is the strategy that will lead to you writing correct recursion. So if the type of a head is a list, then I want to return flatten head, concatenate that with flatten the tail. And otherwise, right, so otherwise type of head is an integer. So I want to do something like do this plus flatten tail. So we think this is going to work? Yes, sir.
So x's can be a list or an integer?
Yeah, that's like this, right?
Yeah.
So the list could either contain integers or lists, because like when I say remove all the brackets, eventually there has to be something that's like the base field, right? What?
It's just the type that you used to define it had to be a list. X's is a list.
Yeah, this is, well, I'm not passing this a non-list. Where am I passing this a non-list? When you give me a list, I take the head, right? That's an element in the list, right? And I'm saying that head is either an integer or a list itself. But nonetheless, the list was passed into the function. I am never passing this function a scalar, a non-list, right? Here, head is a list. Here, tail is a list. Possibly empty list, but list, right? Okay, so let's see if this works, right? Then I'll give you a doozy after this one. Okay, so let's try flattening 1, 2, 3. Great, let's try flattening 1, 2, 3. Let's try flattening 3, and then like double bracketed 4, 5. Right? So I'd like you to think about how you would have maybe attempted this using a for loop or like some of the more primitive methods. You'd need to be pretty clever, right, to do this in a while loop. And in fact, all you'd be doing is simulating a recursive stack. You would require a while. You'd have to do something while. But anyway, so recursion is a very powerful strategy if you can really get your head around it. So again, just presume the function that you're trying to create is already working for smaller examples, right? Which is exactly the principle of mathematical induction. Right? How do I assert the truth of Pn plus 1 if I'm assuming that Pn is true already? Okay, what else do I got for you? Check. Okay, so a super easy one, and then one that's going to be hard but fun. How can we check if a list of numbers is monotonically increasing? Do you know this term monotonically increasing? It can't stay flat. 2, 2, 2 is not monotonically increasing. 2, 3, 4 is monotonically increasing. So you always have to be strictly larger than your previous element. So monotonically increasing. It's let's say this is a list of ints. I'm going to return a Boolean. Okay, so what do I need? I need base case and recursive step. What is the base case here? Well, it's always the same, right? If not x's, Is an empty list monotonically increasing? Yes, it is. It does not fail to be monotonically increasing. And if you think about it, is the singleton list 1 monotonically increasing? Yes, yes it is, right? Because it fails to not be monotonically increased. So this is the problem, right? Sometimes with thinking like this. I feel it's confusing if you're thinking, does the thing satisfy the property, rather than thinking, does this thing fail to satisfy the property? A list of 1 numbers fails to break the monotonically increasing property. A list of empty list fails to break the monotonically increasing property. So that's the mode shift you have to be asking if this violates the condition, sort of not if it necessarily fulfills it. So keeping that in mind, what should I write here, right? Is an empty list monotonically increasing? Yes, right? And you'll see why it has to be true. So how then, what do I check now? Right? Well, but, okay, so we have to be careful. So you're saying if x is at 0 we want to know if this is increasing. So if it's strictly less than x is at 1, what do I return? No, not yet. What about the rest of the list, right? So I have to return, I need to ask the question, is the rest of the list monotonically increasing? Make sense? Does anyone see a problem with this code already? What if the list is of length 1? This won't work. You'll get an index error at number 8. So how can I fix this? Is a list of length 1 monotonically increasing? So really, it's this. Any list whose length is less than or equal to 1 is a monotonically increasing list. Thereby, we can't hit 7 if the list is not at least length 2. But this, I think, should be working already. So let's give it a go. So is this a monotonically increasing list? Should be yes. Is this a monotonically increasing list? Oh, I never returned false. Oh, where do I return false? Oh, here, else, return false. Yeah. Is this monotonically false? Is this monotonically increasing? True. Okay, so let's see one thing. Suppose we wanted to do this, right? You're like, no, professor, no, lecturer, I really am irritated that you said singleton lists and empty lists are monotonically increasing. I'm going to put false there. What's going to happen now? Right? Literally everything we're going to give this is going to end up being false, right? It'll never be true, right? There's no branch here that will ever return true, right? Because another way of writing this would be like this. It needs to be, so I can save this by doing this. So a list is monotonically increasing provided its first element is strictly less than its second element and the rest of it is monotonically increasing. And because of that and false is always false. Right? So if I was always anding and this bottom thing was false, you'd be doing a bunch of stuff and your final thing would be and false. And it would always be false. Right? So it sort of has to be true in this case. Sum the digits of a number. 1, 2, 3. The sum of the digits 1, 2, 3 is 6. How can we do this recursively? So what should you be thinking here, right? You should be thinking, how can I solve this problem if I could solve a smaller problem? So how could I get the sum of something that's 3 digits if I could get the sum of something that's 2 digits? Right, so it's something like, if I could extract the 3, then it's just the sum of digits of 1, 2, right? Or you can do it from the other direction. I can pull off the leading 1, and I can say it's 1 plus the sum of the digits 2, 3. Okay, how do we code this up, though? We have to be a little bit clever. And I don't want to convert to a string and then back. That's cheating. I want to stay in integers. Okay, so, no, I'll just call it foo. So you're going to be given an integer, and you're going to return an integer. And this is going to sum the digits of x. Okay, so what's the base case here? How can I check that? That could be true. That is true, but that would require me to import the math library. Because in order to deduce if a number has one digit, we need a log. So I want to try something else. So maybe this time we'll do the base case last, because it will become apparent once we do the inductive case. So if base something, okay? So we'll come back to this. Okay, so otherwise, what do I want to do? So you have x, it has maybe 5 digits. How can I get it to be 4 digits? Sorry, someone say? Floor division of what? Not n. Oh, 10, yes. Okay. So I want to do a floor division, foo, of x divided by 10. Look at this. Right? So if I have 1, 2, 3, and I divide it by 10, by integer divide, you get 1, 2. Right? So integer dividing it by 10 sort of moves the decimal over. So we succeeded in taking our number and reducing its number of digits by 1. Okay, how do I now get the 3? Modular, right? Because this is quotient and remainder, essentially. So 1, 2, 3 mod 10 is going to give me 3. So I want to do sort of x mod 10 plus the sum of the digits of what remains. Okay. That means eventually I'm going to get a 0 here, right? Because you'll be given something that's a single digit, and then you're going to floor divide by 10, and you'll get 0. So the base case in this case can be if x is 0, in which case I just return 0. So let's see if this works. Foo of 1, 2, 3, 6. Foo of 1, 2, 3, 4, 5, blah, 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 32. So see? See how easy we can program if we're using recursion? This is literally 2 lines of code, right? Gets you something that probably would not just take merely 2 lines of code before we were given this technique. Right, so this is very powerful if you can work your way into thinking inductively. And if you want to be forced to think inductively, take Comp 3400, which is the class that I teach, where we're limited to this paradigm for the entire. You're not allowed loops in my class. No loops, no if statements. So I've told you in this class the 3 things we need are selection, sequencing, and iteration. In my class, I take those 3 things away and we use 3 other things. So it's quite interesting if you do want to take it. So that was a fun one. Determine if the list x's, oh, and this is the old syntax, I'll have to change that, has a sublist that sums to the target. So suppose I give you like a list of numbers, and I say, from among this list, can you make the target 9, the target sum 9? So in this case, yeah, I can, because there's 3, 5, and 1 in it. And 3, 5, and 1 give 9. I say, given this list, could you make the sum -1? Yeah, I can, because -3 plus 2 is -1. So let's try to do this one, sublist sum. Def. So this would be very difficult to do without recursion, and it's going to be trivial, right, to do with recursion. So we're just going to go through and do, oh, this should be a bool, and I need a target. Okay, so if you have the empty list, what should I return? What is the only sum that we can make with the empty list? 0. So when should I return true if I'm given the empty list? If the target is 0. How do I write that? And don't say if target is 0, then return, right? That's the wrong way of doing it. Yeah, we want to say return target is equal to 0. Okay, so this means we will return true given the empty list and a target equals to 0. The empty sum is 0, so we can make 0 with the empty list. Otherwise, return false. With the empty list, we can't do anything else. Yes, sir.
Return not target.
Huh?
Return not target.
Return not target. That would also work. Yeah. We went with that one instead. I know somehow I prefer this one, but this is sort of a I guess you're right. I really should return not target. That's more Pythonic. Yeah, I don't know. You're right. I reluctantly feel that you're right. But this is just doing the same thing, right? This will return true only when target is 0. Okay, so what's the inductive case here? I'm trying to make target in x's. So how could I use the function itself to solve this? Assume it's working already. How can I use it to solve this problem? Okay, I'll give you half the solution. So look at the head of the list. The head of the list is either included in the sum or it's not included in the sum. That's the only two options, right? We're either using it or not using it. Agree? In the case where we're not using it, then our only option is to make the sublist sum in the remainder of the list to get the target, right? So that's me not using the head of the list, right? If I can't use the head of the list, so can I make the target? Can I make the sum of the target in the remainder of the list? What happens if I do use the first member of the list? Right, so I remember I said you either use it or you don't use it. So what happens if I use it? Exactly. I need to make the sublist sum in the remainder of the list of target minus that. If I'm using it, if I'm trying to make the target 6 and I've used 1, then I'm trying to actually do the target of 5 in the remainder of the list. Does that make sense? So let's see if this works. I don't know why my linter is getting mad. What? Oh, what the hell? Yeah, that's why you got to be careful when you submit your stuff to Gradescope. VS Code sometimes does funny stuff like this, and for the life of me, I can't figure out why. It thinks it's helping, but it's not, right? Okay, so sublist sum. Can I make... Okay, so what's a target that I can make in here? I can certainly make 5. Yeah. I can't make 8. I can't make anything that's a negative. So that's working. 2 lines. Which is usually what recursive functions end up being, right? Because you need a base case and an inductive step. So you can really do most of this stuff in 2 lines. This is not even the funnest one I have today. There you go. Suppose you're standing on a grid, and you're only allowed to move along the x-axis and the y-axis in positive directions, and you're never allowed to step backwards, right? So you can either you can step forward by 1, or you can step right by 1, but you're never allowed to move left or move down. Suppose I start you at 0, 0. How many distinct paths are there to x, y? Write me a function that computes the number of distinct paths to x, y, given these restrictions. Do you want to think about it, or you just want to go through it? Okay, 5 minutes to think about it, because it's not overly useful for me to solve all of these for you. So take 5 minutes, because there's really... Actually, no, let's do it together, because the next problem is something that is super interesting, and I really want to get to it. But you do have to help me. So let's try to solve this one. Let's just call it foo. And we're trying to get to x, y. And we're going to return an integer as in the number of paths. So we always need 2 things, right? Base case and induction. What's the base case here? Pardon me? Right, so how many distinct paths are there from 0, 0 to 0, 0? Thank you. Yes, 1. The empty path, right? Not 0, right? Because you think about it, I end up having to describe a path as a sequence of moves. And I can say, here's the empty sequence of moves. That should be a valid move state. Okay. So if not x and not y, then 1. Return 1. Right? Or maybe I can clean this up a bit. In this case, this would be allowable. It may be more expressive. If xy is the origin, then return 1. Okay, so that handles the base case. What's the inductive case? Well, think, what are all your options at this point in time? I can either walk positively by 1 in the x direction or positively by 1 in the y direction. So how do I like use that here, right? So I say it's the number of unique paths from, and this may be confusing, but let me write this. So I'm kind of pulling the grid position towards me. I'm saying I've walked positive in the x direction, and another way of saying that is actually like the target itself has shifted 1 back, right? So it's you have to think of it, rather than you walking to the target, you're sort of like shifting the grid underneath you, so the target's coming to you. So I can either shift the whole grid left by 1, or I can shift it down by 1. Now, that means I need some extra base cases here, right? Because if it's ever the case that x is less than 0, that's illegal. Or if y is less than 0, that's also illegal. But I think this should already work. Okay, so let's think. So to get to 1, 2, how many paths are there? Well, let's do the easier one. To get to 1, 1, how many paths are there? 1, 2. So let's see if this works for 1, 1. Okay. If I want to get to 1, 2, how many paths are there? I have to make sure that they can see 2. So over 1, up 2, that's 1. Over 2, over 1, that's 2. And then the one where I go up, right, up, that's 3. So this should be 3. Right, and it should be commutative. Right, so I don't know, how many paths are there to 12, 9? That many. 293,930 ways. Okay, I'm just going to keep doing recursive problems. I'm going to do so many of them that eventually you'll get it. And this one is an exceedingly cool one. Does anyone know this game or this problem? Anyone heard of the Towers of Hanoi problem? Cool. Okay, so here are some slides I made for my other course. So just don't be afraid that this says functional and logic programming, because we're doing a little bit of recursion. So here's the Tower of Hanoi problem. So I'm going to give you a stack of disks and 3 pegs. And the objective of the game is to move the tower from the leftmost peg, which we'll call peg 0, to the rightmost peg, which we'll call peg 2, the middle one being peg 1. And you're restricted by, you're only allowed to move 1 disk at a time, and all disks have to move to other pegs, and you're never allowed to put a larger disk on top of a smaller disk. Those are the only 2 rules. Can you move all of the disks from peg 0 to peg 2? And the answer is yes. But the question I have is more than, is it possible? My question is, give me the moves. Write me a program that will return the sequence of moves to solve this. How can we do that? Okay, so let's put our inductive caps on. Okay, if we're going to solve this inductively, or if we wanted to sort of prove that a solution does exist, what are the parts of induction? So is it possible to move a stack? Do I have this? Oh. So suppose I wanted to show that it was possible, right? And so that's sort of the exchange here, right? And using induction, you show that the solution exists by building it. And then when you pull it into programming, the procedure actually returns the solution. So if I wanted to say Pn is the proposition that a stack of n disks can be moved to an arbitrary pole, it makes it a little bit easier if we say can we move the stack to any of the pegs rather than just the last one? That actually simplifies things because it's less constrained. But certainly if we can move it to peg 1, we can move it to peg 2. So can we move the stack of n disks, moving one disk at a time, such that bigger disks are never stacked on smaller disks? So what is the base case? Well, is it possible to move 0 disks from an arbitrary peg to another peg? Yeah, what's the move set? Empty. Here's the collection of moves. There are no moves. All right, have a great day. Yeah, you win. So this is called the vacuous case, right? This is sort of like the false implies anything is true sort of case. Okay, here's the induction. Assume that we can move a stack that's 1 shorter, right? To move a stack of n disks, presume we can move n minus 1 many disks. So if I can move n minus 1 many disks, like suppose I could move like you can move the top disk and you can move the bottom stack. Now it's a whole stack. How can I get this from the left side from peg 0 to peg 2? Gotta think inductively. I'm telling you, so there's what? There's 1, 2, 3, 4. There are 5 disks here. And I'm saying you're allowed to move the bottom 4 as a group. So knowing that you can move the bottom 4 as a group, how can I get the disk to the last peg? Yes, sir. Move the small... Oh, okay. You would be right. Sorry, I inverted the way that I grouped the pegs. Okay, so he was correct for what I stated, but it turns out... Okay, so you move 4 of the disks to the middle peg. Then you move the last disk over. And then you move those 4 over there. And what I'm trying to say is that that's enough to write a program that's going to return the solution. That's all we need, right? Because how are we going to determine how to move those 4 disks to the middle peg? The same way, right? By saying, well, let's move 3 of them to the middle peg, and then the bottom one to the last, and do it the same way. So, whoops. Well, this is the solution in Haskell. So don't try to run this in Python, because yeah, it won't work. But anyway, so here I want to write a program now in Python that's going to return the following solution. So one problem in computer science is even how we're going to express the solution once we find it. So here's how I recommend that we encode this problem. Let's call a move. A move is going to be a pair. And the pair is going to be, in the first position of the pair is going to be the number of the disk. And the second position is going to be the peg number. So the first move sort of is encoding, move disk 1 to peg 1. And then move disk 2 to peg 2. Now move disk 1 to peg 2. Right, so then we can continue like this. And as you see in the procedure, we've hit the inductive case now, right? Here's the short stack in the middle. There's the big disk moving, and now the remainder of the moves are just moving that stack back there. Okay, so the question is now, write a program that returns a solution to the Towers of Hanoi problem. So let's give it a try. Define Towers of Hanoi. So what do I need as inputs here? I want to move this many n disks, which is going to be an integer, and I want to move these disks from this peg to this peg. And this is going to return a list of tuple, right, which are going to be the moves. List of tuple. And we just have to remember, okay, so this is move n disks from peg to peg to peg. Okay? And assuming their disks 1, 2, 3, 2 n disks are stacked properly on peg from peg. Okay, base case and recursion. What's the base case? What is the smallest problem in this problem? Pardon me? 0 disks. Okay, so if not n disks, What is the move set? To move 0 disks from peg to peg. There you go. Empty collection of moves. Okay, so that's sorted. Okay, so now we have to sort of like encode what we've like deduced the induction to be. I want to assume that I can move most of these. I want to assume that I can move n-1 disks somewhere. So how can I use that? So let's move, or get the collection of moves to move n disks minus 1. So this is going to be now sort of the top of the stack. So if we had like 7 disks, I'm going to say move disks 1 through 6. And where do I want to move them to? So in like our original picture, I was saying the middle peg. So what's the middle peg here? I have a from peg and a to peg here. I need to figure out which one of these it isn't. Right? So yeah, I need like a sort of off peg. Right? Off peg. So from peg and to peg are going to be one of the numbers 0, 1, and 2. I need off peg to be the other one. How can I get it? And this is where I want to prove to you they need to think rather than code, right? Because you can use math in programming. Yeah.
2 minus from peg minus 2 peg.
Close, but no. 3. Right? Yeah. 3 minus from peg minus 2 peg. Think about it. Okay, so if the from peg is 0 and the to peg is 1, the off peg is 3 minus 1 minus 0, which is 2. That's correct. If the from peg is 0 and the to peg is 2, then 3 minus 2 minus 0 is 1. That's correct. If the to peg is 2 and the from peg is 1, 3 minus 2 minus 1 is 0, right? So this off peg is going to be the peg which from peg and to peg isn't, which you can just think of as the middle peg if you would like. So I want to move n-1 disks to the off peg. And then I want to move the last disk, the largest disk, to the off, like to the to peg. Okay, so it's like I've taken the top of the stack, I've moved it to the middle. I've taken the biggest disk, I've moved it to the end. And now I need to take the stack of disks that are in the middle and move it to the end. So I need to take that again. Okay, I need to move n-1 disk. Oh, I'm missing some stuff. Yeah, hold on. I need to go, yeah, from this peg to the off peg. Hold on. And I'll just put some brackets around here so I can do this. I want to move n-1 disks from this peg to the off peg, and then I want to move the largest disk to the to peg, and then I want to move the n-1 disks from the off peg to the to peg. And then I need to return that. And my assertion is that this is it. This will return a solution to the Towers of Hanoi problem in like what? 3 lines? So let's see. Python interactive sandbox. Okay, so Towers of Hanoi solution. Let's move 3 disks from peg 1 to peg 2. Hooray! Oh. Ha 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 ha. Yes, don't make my mistakes. Okay, thank you. I spelled something wrong. Disks. Oh, it was even highlighting it for me kindly. Let's try again. Okay. So there's 3 disks labeled 1, 2, and 3 on peg 0. So we're all going to have to use our imaginations now. So I'm saying move the smallest disk, disk 1, to peg 2. Move disk 2 to peg 1. Move disk 1 to peg 1. Move disk 3 to peg 2. Then move disk 1 to peg 0, 2 to peg 2, 1 to peg 2. There. The tower has been moved from peg 1 to from peg 0 to peg 2. Yes, sir. Oh, I wonder what would happen in that case. That's a degenerate case. Yeah, I'd have to. Yeah, so this sort of assumed. Well, this assumes a lot of stuff, right? But yeah, I guess a precondition would have to be from peg is not equal to peg. Right, but I could just write a bunch of different edge cases, right? Because I guess in that, if from peg and to peg are the same, you don't want to do anything. You just want to return empty. So we could have made that a base case, for example. Impressed? 3 lines of code to get the solution to Tara's Hanoi problem, right? So again, recursion is very useful for solving problems that seem very complicated, right? In a very compact manner. Like the trouble is just figuring out the induction, which can be tricky. Okay, so that was a fun one. Okay, so just to finalize today's lecture, I just want to teach you a little bit about this dynamic programming. So one problem with recursion is with its efficiency. As we talked about, it has to create all of these recursive stacks, and worse, we've only done something called like linear recursion, where recursive calls are only making one recursive call. We can have other problems where like multiple recursive calls are made at the same time. Fibonacci numbers are like this. This is what we're going to look at, right? The Fibonacci numbers require 2 recursive calls to generate the next number. So there's going to be a strategy where we cache previous results that turns recursions, which are like super slow and memory inefficient, into something super fast and memory efficient, right? So this is a very powerful technique. It's one of like my favorite programming techniques. So we're going to do a little case study on the Fibonacci numbers. Does everyone know what the Fibonacci numbers are? It's like they sort of model the number of bunnies that you get on an island if you allowed them to mate. But it's essentially the nth Fibonacci number is the sum of the previous 2 Fibonacci numbers. And the first 2 Fibonacci numbers are 1 and 1. So let's give that a go. So let's just get the nth Fibonacci number is an integer. So let's just say this returns nth Fibonacci number. So what am I saying? I'm saying if n is equal to 0, or I guess if not n or n is equal to 1, this is where you get stupid statements like this, which I'm going to say like this. So this is actually like 2 cases here. Then return 1. Else I want to return fib of n minus 1 plus fib of n minus 2. So let's take a look here. So fib of 3, that should be 2. Or is fib of 0, 0? Oh, 1. Okay, so fib of 2 should be 2. Then fib of 3 should be 2 plus 1. Okay, let me do it like this. Fib of 0 is 1. Fib of 1 is that. Fib of 2 should be the sum of those 2 previous things. Fib of 3 should be the sum of the 2 previous things. Fib of 4, and so on. You see? Okay. So I'm going to do this. So let's import timing. This is going to allow us to time a function. Why is this yellow? Is this not installed? Oh, boy. Maybe I install it. Okay, that should have, hopefully that will correct things. Okay, we're okay. Okay, so this library is going to allow me to time stuff. So the way that allows me to time stuff is like this. So I want to say timing dot time it. And then I need to give it a function, but you could ignore this lambda for the time being. So I'm going to say time how long it takes to get fib of 10. And then this usually does this like 100 times and takes the average. But for this, I'm just going to say it once, right? So it'll really tell us how long it took to do fib of 10 once. And hopefully this is going to work. Oh, I need to print this. Okay. So let's give this a go. Oh, Lord. I thought it was time it. I thought I did this yesterday. Okay, so just give me a second. Time function Python, right? I could have sworn it was time it. I know I'm very close to, I could have sworn it was time it. Oh, I imported timing. I needed to import time it. That's why it didn't exist. Okay, let's try this. Okay, so this is reporting seconds. So Fibonacci of 10 took, I don't know, 0.0002 seconds. Which is, like, that's not that fast, right? We expect everything on the computer to be measured in milliseconds. Let's try 20. Okay, let's try 30. Oh, you already see that it hiccuped a bit. It's already 0.2 seconds. Let's try 40. Okay, so the point is, right, this is not fast, right? I am waiting for my computer to do something, and likely it's like utilizing 100% of my resources. So I'm going to continue letting this run, and in the meantime, I'm going to show you how we can fix this problem without having to change the fact that we're using recursion. Okay, so 27 seconds it took to get fib of 40. Okay, and the reason is because we're repeating a hell of a lot of computation. Like, if you think how many times fib of 17 is going to be calculated, it's going to be a lot of times, right? Because every function is going to be trying to get the previous two Fibonacci numbers. And since they're always just discarded, we're going to be doing a lot of repetition. So what I want to do instead is give Fibonacci something called the cache, like to let it remember anything that it had previously calculated. So I'm just going to call it like this, fib cache, and it's just going to be a dictionary. All right, and the first thing I'm going to let the Fibonacci number do is I'm going to say if n is in the Fibonacci cache, don't calculate anything. Just return what's in the Fibonacci cache at n. Else do compute something, but save it. And then just go ahead and return it. Okay? And actually, something that we can do is I can just encode the base cases directly into its dictionary. So I can just say, look, I'm just going to tell you that 0 goes to 1 and 1 goes to 1. I'm just sort of loading the base cases into its fib cache. Okay, I'm going to run this again. Barring any errors in the code. Sorry? I think it's fine. I'm timing the same thing. Yeah. Okay. When I didn't do this with caching, it took 27 seconds. So are there any guesses for how long it's going to take now that I've given it a cache? Like 10 seconds, 5 seconds? Now it took as fast as the very first example we did on fib without a cache. Like that was like this, as fast as like getting fib of 5. Okay? So we've totally eliminated the problem that was created by using recursion here, simply by like giving it a cache. And in fact, this caching here, you'll learn in higher levels about something called a decorator. And there's a decorator called memowise, which are called like this, which automates this caching. So it turns out all you have to do is write a recursive function, write at memowise above it, and you get this dynamic caching for free, or automatically, I would say. Okay, so this notion of like using recursion, mitigating the memory and timing issues by giving it a cache is called dynamic programming. And you're going to learn much more about dynamic programming in your third years, but it's an extremely effective way of solving problems. So I think that's all I had for today. So next week is last lecture. Last lecture, we're going to talk a little bit more about timing functions and what it means for one function to be better than another function. I'm going to teach you a little bit about functional programming, and then I'm going to release you to the wild, right, to do what you will. But I'll see you guys next week, right? Okay, chat, thank you for being with us today. I hope you guys have a pleasant week. Sorry for always ignoring you. Oh, I'm sorry I'm so bouncy today. Yeah. That's probably going to even bother me now watching the video. Okay. Bye, guys.